Hello, my name is Shinhae and I'm from KAIST. It is my pleasure to present our work titled Analysis of Blockchain Smart Contracts, Techniques and Insights. I want to start my presentation with some basic concepts, starting with blockchain. Blockchain, as the name indicates, is basically a chain of so-called blocks. A block is a data structure that stores transaction information such as Bob transferred $1 to Alice. The blocks are chained sequentially, and each block has the hash value of previous block data. This mechanism ensures that blockchain data is immutable, as modifying a part of block data requires updates in all consequent blocks, which is computationally invisible. We'll see more details in the next slides. Blockchain is built on top of a P2P network, where each node has a copy of the exact same chain. So let's imagine a case where Alice transfers $1 to Bob. The network nodes first create a block on their own. They select transactions to be included in the block and arrange their order. And here we assume that our transaction was selected as well. Then they start solving a cryptographic puzzle, which is finding a nonce value that, when hashed together with the block data, makes the hash value significantly small. This task is computationally expensive, and as modifying a part of block data requires resolving these puzzles for all consequent blocks, blockchain is considered immutable. Out of the network nodes, the one who first solved this puzzle broadcasts its block. The remaining nodes validate the received block and append it at the end of their chains. By this process, all the network nodes can always remain in a consensus. A smart contract is basically a program implemented in programming languages and deployed on the blockchain. It is invoked by external parties or other contracts, and when invoked, automatically makes transactions. Example code is a game contract that aims to hit the jackpot. If Bob invokes the play function and luckily hits the jackpot, it automatically makes 2 transactions at line 29 and 30 respectively. The first transaction is for Bob to transfer fee amount to the bank, and the second transaction is for the contract to transfer the accumulated jackpot to Bob. As contracts also can hold balances, transfers from contracts are possible as well. While smart contracts have enabled blockchain applicable to various domains such as finance, business, and IoT, they have suffered from a variety of security vulnerabilities. Out of many known vulnerabilities, this table presents so-called exploitable vulnerabilities. These are the ones that have already been exploited or known to be exploitable. While each vulnerability can directly result in a financial loss, we explain 2 vulnerabilities that led to losing the largest amounts of money. The first one is reentrance, which an adversary re-enters the function and continuously transfers money to himself. If you look at the code, the contract transfers the amount to the adversary at line 15. However, when a smart contract transfers money, it calls an unnamed function of the receiver called fallback function. If the adversary recalls the withdraw function in fallback, the transfer can take place again, as the balance of adversary was not yet updated at line 17. This loop continues until the contract becomes out of balance. By this approach, an adversary stored $50 million in 2016 and made the most popular blockchain Ethereum fork. The second vulnerability is called delegate call. It's an instruction that delegates tasks to the callee contract, but under the context of the caller. When an adversary calls init wallet function to the wallet contract, since the contract does not have init wallet implemented, it delegates the call to a wallet library contract. The library then executes its init wallet function, which is to reset the owner of the wallet contract. By this approach, an adversary reset the wallet owner as itself and stored $31 million in 2017. As a result of such vulnerabilities, there has been a research boom in smart contract analysis. Our work presents the first comprehensive survey over smart contract analysis research. We first collected 391 academic papers that contain related keywords such as smart contract and blockchain. The papers range from published materials in top-tier conferences to not yet published materials from online archive. And then, by examining each one closely, we extracted 67 papers that are related to smart contract analysis. The figure shows the overview of our classification. A variety of techniques have been applied in smart contract domain, and most research have targeted Solidity contracts and EVM bytecode. Solidity is the most dominant programming language for Ethereum smart contracts, and compilation of Solidity produces EVM bytecode, which is the actual code deployed on Ethereum. We here introduce three interesting trends of smart contract analysis. The first one is that the portion of static analysis is almost twice as that of dynamic analysis. Static analysis is meaningful in smart contract domain as contracts need to be audited before deployment due to the immutability we have seen in previous slides. Also, as static analysis is based on abstraction, it can reason over all possible paths. On the other hand, dynamic analysis is meaningful as well, as many contracts do not have their source code available. Analysis in bytecode level can result in precision loss due to lack of information such as variable types. Also, as dynamic analysis is based on concrete executions, it does not suffer from false positives. The second one is the most dominant techniques, which are symbolic execution, model checking, and formal verification. While symbolic execution suffers from scalability issues as program sizes increase, it fits well in smart contract domain as contract code sizes are usually small. Also, model checking has been dominant as it enables modeling of execution environments such as external parties or blockchain states. Lastly, formal verification using theorem provers or K-framework has been dominant to guarantee the highest level of correctness. The last one is that the large portion of work is to detect vulnerabilities, following the fact that smart contract vulnerabilities are directly related to financial losses. In the left figure, a ladybug indicates that an analyzer has targeted exploitable vulnerabilities that we have seen in the previous slide. And the right figure shows which analyzer has detected which exploitable vulnerability. While different analyzers have targeted different vulnerabilities, reentrancy has received the most attention. As the last part of our research, we here present insights obtained from the survey. Particularly, we introduce 3 open challenges and 4 promising research directions. We explain details in the following slides. The first open challenge is ambiguity in contract behaviors due to 3 factors. First, as seen in the previous slide, miners have control in the order of transactions. If a user makes a transaction expecting a certain state, it might not be the case if a miner puts another transaction first. Also, smart contracts often rely on off-chain sources such as websites and make use of Oracle contracts as bridges. For example, the contract requests to the Oracle for the current Bitcoin to US dollar rates from an online website at line 20. The Oracle contract handles the request and response by passing the rate data to the callback function at line 12. However, unauthorized sources have possibility to provide wrong data, resulting in unexpected execution results. Lastly, if contracts interact with other contracts that have no source code available, contract behaviors can become ambiguous. The second open challenge is unstable language semantics. The most dominant language, Solidity, has very frequent version releases and often undergoes semantic changes. The code below shows some of the challenge changes made in version 0.5.0 release. At line 4, the address type was divided further into the address type and the address payable type, depending on whether the address can receive money transfers or not. At line 6, the constructor keyword was first introduced, and at line 13, the visibility of fallback function was changed to external. Languages other than Solidity often do not even have language specifications. The last open challenge is lack of clear definitions of vulnerabilities. Existing analyzers define their own patterns to detect, but they do not necessarily imply vulnerabilities and result in high false positives. For example, an analyzer reports a transaction order dependency if there exists two paths with different either floors. The example code was detected as it has two such paths that reach towards line 11 and 20 respectively. However, it was a false positive as there was no difference in the final outcome. This analyzer reported 30% of false positives for transaction order dependency. The first promising research direction is to design new languages. As discussed in previous slides, languages that provide fully specified semantics would contribute to more precise analysis. Also, although most languages are statically typed, they do not conduct strong type checking. In the example code, the bar function does not check the actual type of its argument. So, various scenarios are possible, such as no code execution if Alice variable is not a contract address, or execution of arbitrary full function if Alice variable is an address of arbitrary contract with full function implemented. Therefore, enriching existing type systems can be another promising research direction. The last two directions are machine learning in rising platforms and languages. Applying state-of-the-art machine learning techniques may improve scalability and accuracy of smart contract analysis. And considering that blockchain ecosystem is still evolving very fast, research on other platforms and languages other than Ethereum, Solidity, and EVM bytecode seem promising as well. This is the end of my presentation, and I appreciate for your listening.